course, lecture of the abacus. In this session, we are talking about the 3D designing. As you can see, this is the sample of tensile test with the dimension. I will send you this PDF by the email also, and we are going to simulate uniaxial tensile test, and actually in a high temperature like 360, with some conditions which I explain in a simulation with abacus. So the point is, as you can see, this is the tensile sample. We can simulate the whole sample. I mean, we can draw this. However, you can draw this through the SolidWorks and then save it as an IGS and then import it through the abacus by just right clicking here and then import and then changing this to IGS and then find your file. You can import it here. And like I said, you can also draw this here, but let's talk about how to simulate this. First of all, as you can see, this is the asymmetry part. It means that if I draw a line from this point to this point, I can divide this specimen to two parts, which is symmetry of each other. And if I also draw a line from here, this side and this side is also symmetry. So 1/4 of this would be enough for simulation. And for simulating this, however, there would be some extra boundary conditions, which I will explain. So try to draw 1/4 of this into the abacus part. I'm not going to go through the abacus part and show you how to draw it, because I think you already know how to do it by using the previous lectures. But I already draw this through the SolidWorks, and then this is very easy. I mean, 1/4 of this, and you have every dimension that you need. So just try to draw it, and then everything is fine. So let's go to the abacus. As I said, I already have this file. So tutorial, and then IGS. So, and the point is, these dimensions are millimeters. So the property you have that I already shared you is correct. That gives you the megapascal in the results. So don't worry about the dimension if you are drawing this into the SolidWorks. So noise scale and name is tensile, and then okay. So waiting for importing. Oh yeah, this is the whole thing that I already draw. So how can I can also make it 1/4 here. This is also very easy. If you also draw it like this, you can also make it 1/4. But how? So let's go to the create cut extrude, and then choosing this surface and this line. So we just need to let me go back and explain how I want to do it. I want to cut this from here to here, so I just need to create a plane to draw a plane here, and then as to cut it to half of this, and then the next time would be cutting from this section to the half. So let's do it together, you will understand. So choosing create cut extrude, using create cut extrude, and then choosing this surface, and then ask you one line, it should be vertical, and I'm gonna draw a plane which is bigger than this surface, so it doesn't matter the dimension, just draw it, and then clicking done. So as you can see, this direction shows the direction of the cutting, but how much blend. So how much? I'm gonna use this one. So 120 millimeter. It means half of this 60 millimeter. 60 millimeter is 0.6 centimeter. So this is based on millimeter. So 0.6, it means 60 millimeter or 6 centimeter. So okay, and then you can see it's already half. And the next step is to cutting from here to here for having the half, or from not from here to here because I need the top. So let me have this, and then choosing this again, and then choosing this surface, and then vertical like this, and then I want to draw something bigger than that, and then done, and then you can see it's gonna divide. It's going to cut extrude this from this plane to here. So how much? I'm gonna see it again. 25 means 12.5. 100. Blend again. 125. And then by choosing this one, by entering this dimension, uh, and clicking OK, you can see it's already the half of the pure sample. So this is what we are going to simulate as a 3D. You can also use the this drawing, and then by extrusion, it means you just need to draw this plane. As you can see the dimension here, just choose the 1/4 of this. By the way, I just remembered that the distance between the center of this circle to here is 10 millimeter. So remember this. From the center of this is my mistake. I forgot to mention this part. The center of this circle to here is 10, and also the same if we want 10 from the center of this circle to here. And try to draw the 1/4 of this sample by just drawing the 1/4 of this like this, and then extrude it through this direction for how much? For 1.4 millimeter. So we have the part. Let's go to the property. As I said, you can use the property that I already shared with you. I'm just gonna name it as a steel, and the density, I'm gonna watch the file that I already have as a property. So as you can see, the density is this much. I'm gonna copy it and paste it here, and then going to the elastic part. So the Young modulus is this much, just copy, and the Poisson ratio is 0.3. So I'm gonna enter that one too, 0.3. And going to the plastic, the point is in plastic you have to, I already mentioned that this process should, this tensile test is happening, or is can be happen in 360 degrees. So you have to choose the temperature dependent data. So as when you are choosing this, you can see the the temperature column will be added here, and then we have the data we have doesn't have any uh, temperature, but I'm gonna copy it in a probably Excel. Let me open Excel. So I'm gonna copy all of these, bringing this down, holding shift, then copy. So This is the Excel. I just need to paste it into the Excel and then add 360-degree next to it. So you can see this is the data, just 360 here and then 360, and that's it. So like this, and then Control and Shift together and direction down, Control C, and paste it by Control V into the locus. So this is the property that we have to assign it to this part. Clicking OK. Create a homogeneous section, solid, continue, okay, and then assigning this, removing this set, and then assigning this to the part we have. So we already assigned the part, and then the next one, we have to go to the assembly and import this to the assembly, dependent, okay, and the one thing I always do is to adjust to bring this into the, this because we're gonna fix here, and so I'm gonna bring this to the middle of this. To bring this coordinate system to the middle of this edge, and it doesn't matter actually, but later for working with results it might be necessary, so it depends on you. So I did choose this, and then choosing the center point, and then in center 0 0 0, so you can see it's already moved, and then I'm clicking OK, so you can see it's already there. And then the next one is so this is the step, and this process actually that we done here in this institute is the tensile happened in 9 seconds with the speed of 0.1 millimeter per async seconds. I have to check it. I will check it. Let's just check it together. But for creating this step, we don't need the speed. So just create a step. Here, this is the dynamic, so, and also the temperature displacement, because we did apply the temperature, and also it's explicit. So choosing the step kind of or sort of dynamic temperature displacement explicit, clicking continue, and the time period for this one, just because this might take a long time, so just choose as 6 seconds, and or maybe 5 seconds, up to you, because we are going to apply the speed of displacement, and clicking OK. So there is no interaction because there is no interaction, we're gonna fix this side, and it's gonna be moved to this direction, and then going to the load. So let's talk about the boundary condition here. Let me explain something to you. Here in this picture, as you can see, actually this is the 1/4 of this specimen. The point is, we did cut it from the half through the vertical line. It means this section should be the symmetry of this section, as well as this section should be fixed. What I mean is, forget about the 1/4. Let's go through the complete part and see what is the condition for the tensile test. In actual tensile test, one side is fixed. One of these holes is fixed by the tensile machine, and the other side is gonna be moved through the vertical direction. So one side is fixed, the other side is movable. And when we divide this through this vertical line, it means this hole is fixed. It means the boundary condition for this side should be fixed, and also should be symmetry of this section. It means later if you want to mirror this side to this side and also the half, it should work. So let's go to the boundary condition and I will show you here. This is the boundary condition. Create a boundary condition and then name it left, or sorry, right. Surface, and from initial, and it should be symmetry, continue, and choosing the surface and then clicking done. So here there are the available boundary conditions. As I said, this surface should be fixed through the x direction, so u1, and should be also the symmetry, fixed and symmetry through the x, and clicking OK. And also the same situation for this zone, this surface, these two should be symmetry and also fixed through the y direction. So let's now make another boundary condition and then name it bottom. Surface, and clicking continue and choosing this and holding shift and choosing this surface again and done, and then you can see the u2 or y. So as you already know, 1 is x, 2 is y, and 3 is z, and clicking OK. So the last boundary condition, or actually the applying the speed or moving this giving the speed to this area, which I already explained. In actual, the force is applying to this hole and then through this direction. So that means our force or our speed should apply to this surface. And we choose another boundary condition and name it as a speed, and from step 1, velocity, and continue, choosing here and done, and through the it should be in minus x direction. So opening this and then minus, let me check it. This is like I said, I have to check how much speed it does have this one. So 5 millimeter per second. So yeah, it means 0.005 minus because minus of x, and the rest of them should be 0. So we don't like this one goes to any other direction, and then clicking OK. So as you can see, the directions already appeared. And so the next step is that you have to go to the mesh and then choosing part and then meshing here. I already did check for you that you are only able to mesh parts with the student license of the Abacus for 1000, no, 10,000 nodes, as I remember, or 1000 nodes, something like that. So that's why here we are choosing 30 or 3 millimeter or even maybe more. Let me just try it and then see. So this is so rough, so maybe 0.5 and then see. So let me mesh this one. So 75. So we still have, we can still make it final. So 0.1 might be better. So yeah, this is enough. 795, 94. So yeah, if even you, I mean, the meshing, the size of the meshing, it doesn't matter. Okay, the point is your result, the actual result of you can have like for doing the process is not important, and however for research about the or studying the result is really important, the mesh size. But here you don't need to focus right now on just learn how to simulate the 3D. So yeah, don't maybe later if you work with a license, with a actual license of the Abacus, you can do the same with the finer mesh. So yeah, and then that's it. This is the simple standard and simple corrected uh, tensile test. And then you just need to create a job and name it as a tensile, and clicking OK, and then run it. And before running, I already told you that just don't forget to first of all save your uh, design, what you did. So it is really important to save. And I'm gonna save it again here as a tensile new. And also another important thing is to change the set work directory. This is also really important because it's going to be saved automatically into the C temp. So what I always do is to make a direction to the same folder that I already saved my design. And then you can see in the lecture there is a ODB. I already create this ODB file. So if you don't have this, just create a new folder and then name it ODB and then mark it like I did, and then click OK and then OK. So now the result of this gonna be saved into the ODB file. So yeah, try to design this, try to work with this video. I'm gonna upload this as soon as possible, and try to, if you face any error or any error during the simulation, first of all try to solve it by yourself. If you couldn't, try to Google it and then solve it. If you couldn't do it, we can face your problems next time into the actual lecture. I will email you regarding to the next session of our lecture regarding to the Abacus. So yeah, have a nice day and see you very soon.